Okay, so we have no. Okay. Okay, good. Now right. So we can start today's seminar. I will let Fred introduce our speaker.
Good morning, everybody. So we are very happy to have the visit of Anamaria Gkini. Up to the end of May here, we are working on superluminous supernovae with a few people, including Ismail here. And Anamaria did a Bachelor of Physics and a Master in Greece. Then she moved to Stockholm, where she did her PhD, which defended a couple of months ago in February. So mainly the project, her PhD was on superluminous supernovae, looking for signatures of disruptive mass loss in superluminous supernovae. And I guess you're going to discuss a bit of this subject.
Yeah.
So the floor is yours.
Perfect. Thank you for pronouncing my surname correctly. So hello to everyone. Thank you so much for having me here today. I'm visiting IAC or IAC for a few weeks, and I would like to present the work that I did most of my PhD in Stockholm, which is about what the near-ultraviolet spectroscopy can tell us about the final moments of the progenitors of supernova. Supernova is a phenomenon that I guess you're all very familiar with, but it's not something that we have detected recently. It has been seen for thousands of years from people that they were observing the night sky, and they were seeing that there are some new bright spots that they were not there before, lasting for a few weeks or months, and then they were disappearing forever. And they were calling them guest stars for this reason, because they were coming and then fading within a few weeks. So now we know that these guest stars are supernova that are terminal explosions of stars. Here we see some of the supernova remnants in our galaxy, that some of the most famous one. You are all familiar with the Crab Nebula, with Tycho Brahe supernova, and Kepler supernova, which was actually the last galactic supernova that we have observed, and that was 400 years ago. Since then, we have not observed a supernova in our galaxy. The way that we detect supernova now, not in our galaxy, but in other galaxies in the universe, has changed a lot since 400 years ago, but also since 50 years ago, because 50 years ago, what people were doing is taking photographs of massive galaxies continuously, and they were comparing these photographs in order to see if there's any new bright spot in the new image, in order to detect some supernova or some transient event in general. This has changed a lot today because we have the time domain surveys, which are sky surveys with wide field of view, that they scan the entire sky at a high cadence of 2, 3, 4, 5 weeks, days, depends. Here I show some of the most famous sky surveys, among which is the Legacy Survey of Space and Time, LSST, which is the most promising survey for us right now, and also the Zwicky Transient Facility, ZTF. No? Yes? Or no? Okay, which I have been part of my PhD, but I'm still part of it, and I have used data from this. So what these sky surveys, they do is that they literally taking multiple photos of the sky when they start operating. And also after this at the high cadence. Here we see the CCD, or the camera of ZTF, which has a field of view of 47 square degrees. You can see that in the camera there are 16 CCDs, and in one CCD can even fit the Andromeda galaxy. And in comparison, you see some of the cameras of other surveys, with LSST being much smaller, 9.6 square degrees, but this is because it will go also much deeper. It is expected to go down to 27 magnitudes in the stack images, while ZTF is going to 21 magnitudes. So what these time surveys do is that when they start operating, they take some reference images, which we use for the subtraction later. After this, they take a lot of science images, they subtract them from the reference images, and what we get at the end is a difference image. Now, if in this difference image we have a detection, Then this initiates or triggers an alert system with a lot of information about this observation. And the photometry of this observation can help us construct the so-called light curve, which is the evolution of the light with the time. And the light curve of a transient event in general has a rise time, it peaks, and then declines until it fades and we cannot see it anymore. But this light curve for now is not 100% enough to tell us what kind of transient event we have observed. And for this reason, we need a spectrum. There are dedicated surveys in order to take spectra and classify these events. Two of them that I have been part of is the Public ISO Spectroscopic Survey for Transient Objects, or PESTO, and the transient survey of ZTF that I have observed for both of them. And in the right, we see a sky map with all the spectroscopically confirmed supernova that had been detected from all the surveys in the sky. And for now, we have detected, or we have classified, more than 17,000 supernova. And the reason why we need a big sample of these events is because we need to establish a theoretical framework. There are two main groups, if I can say, of supernova: the core collapse supernova and the thermonuclear supernova. The talk today will be about core collapse supernova, which coming from massive stars. So we have a star, massive star. In the core, it fuses hydrogen. Eventually, when this hydrogen depletes, it will start fusing heavier elements going through helium, carbon, oxygen, neon, magnesium, silicon, until the formation of an iron core. Now, this iron core cannot be fused further because it would require energy and would not release energy. And for this reason, or for several things that happen in the core, the iron core will collapse, but this implosion will turn into explosion, and all the outer layers of the star will go outwards, and this will have as a result the star to explode, leaving behind a neutron star or a black hole. And this is where we, the observers, see that there was a supernova went off on the sky. But of course, what we see is not a star anymore, but is a composition of the outer layers of the ejecta of the star that is called ejecta. You can see here. And then there is the compact object, the neutron star or the black hole left behind. The star, though, doesn't live a vanilla life. It's going through a lot of mass loss during its life, and it can completely lose a lot of layers, the hydrogen, helium, or even heavier element layers. Actually, we have seen stars stripped down to the silicon layer. Through the same channel, the star will explode, we will see it, but now around the ejecta, there will be some circumstellar material, or CSM, that has been formed from this previously ejected material. There are three main ways of a mass loss mechanism, or three main mass loss mechanisms in the stars. There are the stellar winds, which we have actually seen also in our star, the sun, which the star ejects material also starting from the main sequence. There is the binary system, stripping, in which our massive star is in a binary system with a companion, and the companion accretes material from the massive star, removing some of the outer layers. And there is also the eruptive mass loss mechanism, in which the star suddenly loses a lot of mass during the late stages of the stellar evolution, more advanced nuclear burning, carbon, oxygen, silicon. It's not really well defined yet. And here I showed two images of how AI imagine that the binary stripping looks like and an eruptive mass loss looks like. There are various eruptive mass loss mechanisms that has been discussed in the literature, but here I will spend a few minutes to discuss something that is called pulsational pair instability. We have a massive, when I say massive, 30 to 65 solar mass of helium core, which satisfying the criteria, the pair production, electron-positron production from high energy photons. This will remove some of the radiative pressure that was helping to keep the core stable. And as a result, the core will contract, increasing the temperature, and this will lead to explosive burning of carbon and oxygen. And this explosive burning is enough to release energy in order to eject some of the outer layers of the star. This can happen many times depending on the mass of the star, how much it has been ejected, but also on the energetics in general. But the important thing is that this mechanism can form multiple CSM around the star. So you can imagine that we have different kinds of stars, that they do a lot of things during their lives, and this ends up in a zoo of supernova classification. The main distinction is if they have hydrogen in their spectra or not. If they have, they classify as supernova type 2, and there are also many subtypes depending on the light curve shape, if they show some signatures of interaction in the spectra, if this hydrogen that was there disappears later, how bright they are. But I will not really discuss about type 2 supernova. The focus will be in supernova type 1, which means that they do not show hydrogen in their spectra. And there are various subtypes of supernova, supernova 1b if they show helium, supernova 1c if they don't show helium, supernova type 1e, which is a new class of supernova that doesn't show helium, carbon, oxygen, neo doesn't show anything. There are the superluminous supernova that I will discuss later. And also here I show the supernova type 1a, which is the thermonuclear that I mentioned before that I will not touch today at all. What I want you to focus here is that there are this class or subclass of supernova that they have this N suffix here. And this means that in their spectra, we see that there is some signatures of interaction. Interaction means that the ejecta, as it expands, it collides with this CSM that has been formed from previously ejected material. So far, the interaction or the presence of a CSM around the star in general has been manifest with two ways. One way is flash feature of highly ionized elements, carbon, nitrogen, oxygen, that are showing up in the spectra within days after the explosion. And the second one is narrow emission lines of hydrogen, helium, carbon, depending on the composition of the CSM, that persist for weeks. And these are the objects that they take this N suffix at the end of their classification. But the spoiler alert here is that there have been seen an additional diagnostic for the presence of a CSM without necessarily the ejecta interact with this CSM. And these are some resonance lines in the near UV part of the spectrum. And these lines have been detecting for the first time in a class of objects that are called superluminous supernova. And I want to spend a few time explaining and give a brief introduction of this field. Superluminous supernova are transient events that are very luminous, 10 to 100 times more luminous than the normal core collapse. Here we see a comparison of the light curves of normal supernova and superluminous supernova. And we see that they are much brighter, but also their light curves are longer, which could mean that the progenitor stars are more massive than normal core collapse. And they're also very rare. Only 6% of the observed core collapse supernova are superluminous supernova. The reason why we are interested in this field is because there are two main questions we need to answer. First of all, what makes this object so luminous? And second, what are the progenitor stars of these explosions? Regarding the first one, the question is raised because normal type 1 supernova are powered by the radioactive decay of nickel-56 and cobalt-56 that are synthesized during the core collapse. And actually, the peak of the light curve can give us an estimate on the mass of the nickel-56. However, the peak of the superluminous supernova is so bright that it cannot be explained by the nickel-56 power mechanism. And this is because you would require a lot of mass which cannot be synthesized during the explosion. And for this reason, we have come up with some alternative scenarios which can power the light curves of superluminous supernova. The first one is the pair instability, which is pretty similar with the pulsational pair instability, but this encounters for a more massive star, for a helium core of 65 to 130 solar masses. Again, through the same mechanism that I described before, there will be some explosive burning in the core, but now the energy that will be released by this explosive burning is enough to completely disrupt the star, leaving no remnant behind. So this scenario is a theoretical scenario, which can produce the high amount of nickel-56 that is required to power the light curve of superluminous supernova. But there are two drawbacks. First of all, it predicts long rise times because we're talking about very massive star and the light will take a lot of time to diffuse out from the star. And also the current models that exist do not really fit the observations. However, there are a few candidates of pair instability supernova. And the best one, I will mention it a bit later. The second scenario is the magnetar. Magnetar is a rapidly rotating, highly magnetized neutron star that is synthesized or is the compact object that remains from the explosion. The magnetar is, if I may say, the best scenario in the sense that is the scenario where all the people in the superluminous supernova community explore. It fits very well the observations, but this can be bad because it has a lot of free parameters that it can fit everything. So this means that sometimes maybe we should not trust the results that we see. It's good because it can explain some bumps and undulation that we see sometimes in the light curves of superluminous supernova, but it cannot explain some interaction signatures that we see in the spectra. Then there's the CSM interaction model. As I said, the ejecta, as it expands, it collides with the CSM that exists around. And this will create a radiative shock wave, which is able to give this extra energy that is required to power the light curves. It can explain a lot of things. It can explain some bumps that we see in the light curves. It can explain the interaction signature that we see in the spectra. It can explain some late time hydrogen that we see in the superluminous supernova type 1 spectra that, as I said before, there is no hydrogen there initially. But there are not currently models that we can use in order to fit the spectra and the light curve. When I say there are no currently models, I mean there are not really very realistic physical models that we can use. And last is the black hole accretion, where these massive stars you would expect to collapse into a black hole. And accretion into the black hole can create some outflows, which can also thermalize the ejecta. It's a good scenario in the sense that it can also explain some things that we see in the light curve, but in that case, you would expect the inner parts of the star to have been accreted into the black hole. So at the end, you wouldn't really expect to see a lot of iron elements in the spectra, but we have always seen iron elements in the spectra. So we cannot really reconcile this. And also the models that are now, they predict very high accreted mass, order of hundreds of solar masses, which we do not really believe that there are such massive stars that could create something like this. And of course, there are the hybrid models, in which can be a combination of different of these alternative scenarios in order to power these objects. So within this class of superluminous supernova that many people are interested, we have detected two superluminous supernova that they show these resonance lines in their spectra, magnesium-2 resonance lines that are blue shifted by a few thousand kilometers per second from the rest frame. And these lines have been explained by resonance scattering of the superluminous supernova continuum by rapidly expanding CSM. And actually the shift in the lines can give an estimate of how fast this CSM is moving. So motivated by the discovery of these two objects, and in order to try and understand how common are these lines in the spectra of superluminous supernova, we submitted 4 proposals in X-Shooter in order to collect a sample of the superluminous supernova. And we managed to do this. And within this sample, we identified 2 more objects that they show these resonance lines in the spectra. So as I said before, we know that this is coming from a CSM, but we don't know anything about this CSM. We don't know the location. We don't know exactly how fast it's moving, the composition, how thick it is. We don't know anything. And in order to get this parameter and try to link it back to the actual progenitor star, we use a Monte Carlo scattering code in which photons are propagating or emitted from the superluminous supernova photosphere, and they are propagating within a CSM, and they resonance scatter into the magnesium-2 lines. And depending on the properties of the CSM, we can get at the end different magnesium-2 synthetic line profiles Actually, here we see an example of how a CSM that they're moving exactly the same, they have the same optical depth and the same thickness, but they are located at different distances from the photosphere, can change the profile of the magnesium 2. So using this code, we model the two objects that we have found plus 89 dB, which is one of the two objects that they initially showed this. And 89 dB is actually the best pair instability candidate that I mentioned before. And from the modeling, we found that this CSM has been ejected right on the onset of the explosion, which means that these stars eject material only a few months before they explode, and then they explode. This is something that it's the first time that we have seen a direct evidence for something like this in superluminous supernova. So the question we want to answer is, what is the origin of these CSM shells before I explore various scenarios for mass loss mechanism? So let's take them one by one. Stellar winds we do not really explore because the time scales are not really consistent with the stellar winds. As I said, stellar winds, the star start losing mass already from the main sequence. In the binary scenario, in which we have a companion stripping the star, we are not really aware of any model that can give something like this. Something like this meaning a shell created just a few months before the explosion. So the most likely scenario is the eruptive mass loss because it fits the time scale, but also in order to get eruptions at this stage of the burning, of the nuclear burning, you would need a shock wave to be created from the core in order to expel this kind of material from the star. And eruptive mass loss is one of the mechanisms that can do this. Now, in the eruptive mass loss, there are a few scenarios, but the best one in the literature right now that we can compare with is the pulsational pair instability, because it is one way of creating this shock wave that I said in order to eject the outer layers of the star. And comparison with the model show that we are talking about stars that are more massive than 45 and 50 solar mass of helium core, so really massive stars. So we have a massive star that ejects some material, and then it explodes, because what we see at the end is the explosion of these stars. Here we see the light curves of the two objects that I discussed about, the one that we found in the sample. And we try to explore different scenarios to see what powers this object. And the first one, of course, is the magnetar, is the one that we explore. So in the magnetar scenario, actually, the light curve, the model can fit very well the light curve. But the problem is that it predicts a star that has ejected less than 10 solar masses of ejecta. So before I talk about a star of 50 solar masses, and now we find something that has ejected 10 solar masses of ejecta. So there are 40 solar masses missing. So perhaps the magnetar is not the best model to explain what powers this object, but there is also the fallback accretion. And why? Because you would expect such massive stars to collapse into a black hole. So this could be a valuable scenario to explore. However, as I said, there are not really models that we can compare with. But this is more like an open invitation to the modelers to try and understand how this massive star can explode and how can these objects be powered and be so luminous. In this sample, we only found two of the objects, but the rest of the sample did not really show these features in their spectra. And is this because there is no CSM around it, in the sense that this star did not eject anything before they explode? Or is this because they have a CSM, but it produces very weak lines that we cannot really detect within the noise of the spectrum? To explore this scenario, we collected a sample of superluminous supernova that consists from the objects that we obtain with the X-shooter proposal, but also objects that exist already in the literature. And using the code that I described and a grid of parameter space, we produce 200,000 synthetic magnesium-2 line profiles, which we then compare with the observations in order to see whether these synthetic lines would arise above the noise of the spectrum and to put some constraints on the CSM shells. Here is an example of the method that we use. In the left panel, you can see the purple one is the observed spectrum. And the black one is how the synthetic or how the spectrum would look like if a CSM with these properties existed. So in the left one, you see that the CSM shell that is located so far away, it's moving with almost 3,000 kilometers per second and with a high optical depth, it would have created very strong magnesium 2 absorption lines that if it existed, we would have definitely been seen in the spectrum. So we can rule out the possibility that such a CSM shell exists around this star. Now in the right panel, we see that the CSM shell with these properties here would create very weak lines that we wouldn't be able to detect within the noise of the spectrum. So for this case, we cannot really rule out the possibility that such a CSM exists around the star. So of course, this was not done by AI, and it's not possible to do this for 200,000 models. So we developed a model comparison method in order to quantify the significance of the detections within the noise of the spectrum. And we can summarize these results in corner plots, where corner plots show the percentage of the models that are ruled out with more than 5 sigma. And here I show 2 corner plots for 2 different objects, one for a signal to noise in the spectrum of 3.5, and one for a signal to noise of 22. I know that for stellar people, signal to noise of 22 maybe is not very good, but in the supernova is very good because we are talking about objects with redshift of 0.4, 0.5, so it is actually good. And then, yes, and here we see that with increasing signal to noise, we can rule out more models because less and less weak lines would be hidden within the noise of the spectrum, which makes sense. But here, what is very interesting is that even in a signal to noise of 22, shells that are geometrically or optically thin will indeed produce very weak lines that we wouldn't be able to detect even in a good quality spectrum, which means that we cannot rule out the possibility that such CSM shells exist around these stars. Within the sample, and with this method, we identify 2 more objects that they show this line, increasing the sample from 2 to 4 to 6. And they also fall within this month time scale that I showed before. So these stars, indeed, again, they do something right before they explode. Now, if we take a look in the summarized properties of the shells that we have detected, and in particular in the maximum velocity or the velocity of these CSM shells, we see that they are falling within these 3,000 to 5,000 kilometers per second. If we now go into the corner plot, in the first column where we map this velocity, we actually see that we are not sensitive towards any of velocity value in our parameter space, which means that the high velocities are not a selection effect, but is an intrinsic properties of this CSM, that these stars eject CSM shells that are moving so fast. Now, if we go into the inner radius, which is like how close is the CSM to the photosphere, we also see that it is within a narrow range of 1.8 to 2 photospheric radius. And if we go now to the second column, we actually see that we are sensitive towards nearby shells, which means that it's easier to detect shells that are closer to the photosphere than shells that are further. So taking all this into account, the question that we want to answer is why these CSM shells remain undetected. Which of the 2 scenarios that I showed before is the case? Here we see a plot of the column density, magnesium to column density as a function of the signal to noise. The purple shaded area shows the undetected shells or shells that would be hidden at a given signal to noise. And the stars represent the column density values of the shells that we have detected. So here we see that if we had CSM shells with properties similar to the 4 out of 5 that we have detected, then we would have definitely been seeing these shells around the stars in all our sample, which means that shells similar to the one that we have already detected in 4 out of 5 are not present. But there is 1 out of 5, which actually the lines that we detect in the sample, in the spectrum, was so weak that you would require a signal to noise of more than 20 in order to see. So we do see that there is at least one object where it shows these weak lines that we wouldn't have been seen if we had a worse quality signal-to-noise spectrum. So it seems that we are not really able to understand if indeed there are CSM lines that we don't see, or if we were so lucky that the one that there was, we actually saw it. Another way of trying and understand how unique are these stars that they eject these kind of shells is to try and find if there is any correlation between the maximum velocity and the decline rate, or the CSM parameters and the light curve parameters. And we found that there is perhaps a tentative correlation between the decline rate of the light curve and the maximum velocity of the CSM, which, if true, can be a very powerful link between the eruption and the subsequent explosion. But of course, with 5 data points, we cannot really claim a correlation. And this is why we'd be good if we had more data. And this question of why do we not see this CSM, it still remains open. So after this work, there are several questions that have been arose. First of all, are there other lines that we can use in the UV in order to see that it exists a CSM around it? There are some other resonance lines, not in the near UV, but in the far UV and in the optical. The far UV, the problem is that from ground, we cannot really observe this part of the spectrum because it would require very high redshift. And very high redshift, it means we would have very poor signal to noise. So there is a give and take here. But there are also in the optical part some lines, which are the sodium, and the calcium. But these lines are most likely ionized by the superluminous supernova continuum, and for this reason, we do not really see. So for now, the magnesium-2 lines remain one of the best diagnostic lines that we can use for this kind of analysis. Another question is, are such explosions unique to superluminous supernova, or there are also other transients or other progenitors of transients that they can do something like this? So there is not really answer to this question. But for example, gamma ray bursts are expected to originate from massive stars. And for this reason, there is no reason to believe that the stars do not do something like this. So it would be very interesting if a similar analysis can also be done in the GRBs. In which case, can this help us distinguish the different progenitor system for the different transients? If, for example, we manage to identify these lines in the GRB, can they tell us that they are coming from a particular progenitor star that is different from the superluminous supernova, for example? These are very open questions that would be very nice to be explored, but there are no answers for this yet. However, we have LSST, as I mentioned before, and the upcoming Roman Space Telescope, that they will or expect to discover higher redshift transients, which means that from here, from the ground, we can actually detect the near UV part of the spectrum. And we can do this kind of analysis and unlock some of the mysteries that exist around these objects. But this is a work in progress and also future work in general. So I didn't take much of the time, 33 minutes, perfect. Here are my takeaway messages that I would like you to keep from this seminar. First of all, the CSM, apart from the direct interaction of the ejector with the CSM that cause these narrow lines that I mentioned before, can also manifest in the form of these magnesium-2 lines in the near UV part of the spectrum, which shows direct evidence that there is eruptive mass loss at the onset of the superluminous supernova explosions. It's still an open question whether these stars is a subclass of superluminous supernova progenitors that are undergoing this kind of eruption, or if it's a more general characteristic of the massive stars, but for some reason we cannot really see these lines of the spectrum. More data and improved modeling will be able to put some better constraints on the mass loss history and as a result in the progenitors. And also applying this kind of method to other transients can give us some idea if this or similar mass loss behavior is common. Thank you.
Thank you for this very interesting presentation. Do we have questions? Yes.
Thank you for the nice talk. So these CSM shells, when they are erupted, and they often lead to dust formation. So what I expect is the supernova shock to collide with the CSM shell with dust. Can you comment something about infrared signatures of this interaction?
Yes, so we have not really done work in the near infrared. In the X-shooter spectra, they also have the near infrared arm, but it was always very noisy that you could not detect anything, not even in the continuum to see, for example, some rise in the red. But also you would expect that this kind of so in my mind, at least how I understand it, is that there are these eruptions a few months before. These CSM are quite close to the superluminous supernova. So when the superluminous supernova explode, then either if there is some formation of dust, there will be destruction. It will be destroyed because it's quite a warm environment. Or I suspect that there will be the interaction with the eject and there will very fast swept up the CSM. I guess it depends of the optical depth, of how much mass exists. It would be very interesting to search for this in the near infrared. But also there is one case that I didn't mention, the first object that ever discovered, IPTF16EH, which I didn't mention because it didn't have X-shooter spectra. And in this one, the shell was very far away. So in this case, you would indeed expect dust formation, but there was not a study about this.
Okay. So yeah, thank you very much.
Yeah, of course, of course.
Okay, thank you for your Monte Carlo simulations. Do you assume any geometry for the CSM shell? For instance, what will be the importance of the inclination? For instance, if there is like a asymmetric disk or whatever.
No, for this, it's spherical symmetry that we assume in the code. There is some ongoing work in order to include some asymmetry, for example, some disk or some clamps. But so the spherical symmetry, for now, it's quite good assumption because you have some eruption. So you would expect something like this first. And second, in 16EH, the magnesium 2 later from absorption went into an emission. And we were able, or the people that they did this for, were able to find the geometry of the shell, and they found that it was close to spherical. And this is why for now we use this. But there is ongoing work to include more geometries in the code.
Yeah, I asked, sorry, this is like a comment, maybe this is interesting for you, because I asked, because I saw some modeling that actually, some hydrodynamical modeling that actually sort of reproduced by the data with a bipolar breakdown.
Okay.
In actually not superluminous supernovae.
Okay.
So,
but this was CSM interaction, I
Yeah,
guess, right?
yeah.
Yes. Okay. Okay.
even if the eruption is spherically symmetric, it can interact quite quickly. For instance,
Yeah.
if there is like an accretion disk or whatever, and it can produce like a bipolar breakdown quite quickly.
Yes.
Okay. In months also, for instance.
This, I think, would be very interesting for the light curve modeling to understand, why are these objects so bright. So I would take a look at this. Thank you.
Do we have other questions? Yes.
Thank you very much. Disclaimer, I'm not really from this field, so maybe forgive if the question is a little trivial. But you discuss a lot about these models, and I wanted to understand, since they seem to be very based not on really simple physics, right? Based in plasma physics, based on nuclear physics and stuff. So how much these models really come from first principle physics, and how much are just phenomenological model, and how much can we trust that these models really give the signature that we expect given the framework that we base them on, matter, black hole, and so on and so forth.
So the scenario, it comes from first principle physics. What would you expect? The actual models that we use, I would say, are more toy models, are more simple equations that we try to fit in order we need to apply in order to fit the light curves. In the light curve modeling with the spectral modeling, it's quite different. Spectral, because it's spectral synthesis, you would require a lot of atomic physics as well there. It's much harder, and that's why there are not really many spectral models that we can use. The light curve physics, because it's like accumulated light, bolometric, many people use the bolometric light curve. It's simpler, but still it's not really very include like plasma physics. Hydrodynamics are recently models that have include hydrodynamics, for example, in their model. So it's depends on what you try to fit, spectral light curve, I would say.
Okay, and when you comment about, for example, the magnetar that have too many models, like what do you mean by that? Why the magnetar specifically have too many parameters?
It has many, so there are the equations that we use, how the spin down of the magnetar, it gives like the rotational energy, or like the time scale that you would require in order for the magnetal energy to thermalize the ejector. All this, they have a lot of parameters that when we fit the model are free. And that's why we take some results that if you see them, you're like, okay, yes, you can have a magnetar that has these properties, but this doesn't mean that it would create a superluminous supernova in that sense.
But then maybe with follow-up observation, can you maybe have other observation? I don't know, for example, magnetar, I guess, has other signatures like pulsar-like or something like that, that maybe can help to discriminate what really is, or also observation that came before the supernova, if they are available, for example.
There are like late time observations that they could give some smoking gun. For example, in the light curve, you would expect a particular decline rate at later times, that it could be distinguished from the radioactive decay or from the black hole accretion. But, and also in the spectra, there are some lines that you would expect to see from a magnetar. The problem in the supernova is that are extragalactic, and by the time you would want to see these features, the supernova will not be detectable anymore. There are very few that we have taken late time observations, and still we cannot really probe what is the power mechanism.
Okay, thank you very much.
Have in the realm of multispectral, not multispectral, multi-messenger astronomy, this has any signature? These events have signature in the gravitational wave event, or maybe neutrino detectors? Have they been observed and maybe correlated?
So gravitational wave, not as far as I know. We have never detected gravitational waves on superluminous supernova. There are some correlation with the GRBs, in the sense that maybe you can detect some gamma ray bursts from this for superluminous supernova. I think there is one candidate that we have found, or two, one or two, but not really like kilonova, where you would expect the multi-messenger to be like everywhere, gamma ray, X-ray, optical, neutrinos. No, superluminous supernova is not something like this.
Nice talk, Anamaria. I'm interested in you mentioned that there are other UV lines. I mean, which UV lines?
There are in the far UV some oxygen lines, like oxygen 3, 4, 5. There are some carbon lines as well. There are also some Lyman alpha as well. It's a resonance line, but it's very far UV, and we have never really observed something like this. We have a few spectra, HST spectra, but HST is not. So another problem that I didn't mention is the resolution, because you would require a high resolution spectrum in order to be able to resolve these lines in the spectrum. So we have a lot of biases for to detect these kind of lines.
And about the resolution, the spectral resolution, some of the objects you showed, you have very, very broad lines.
Yeah.
So you don't need then the spectral solution. You could do it with normal, whatever, medium resolution.
They are broad lines, but the full width half maximum is around 250 kilometer per second, or like 500, or this, or 1,000, within 1,000. So I still think that you would need a good instrument in order to resolve this line. But resolve these lines, what I mean is to be able to model them in order to get some CSM properties. Because in 16EH, the first object that was detected, we saw that the lines were not resolved. So we were not actually know how broad they were. And we were not able to do this kind of analysis in this object. That's why I still think that you need a good resolution.
A good throughput in the UV.
Yes. Yes, exactly.
Thank you.
Thank you, Anamaria. Very clear talk. So for these few objects, the redshift are quite, for some of them, they are all 0.1, 0.2, something like that.
Yes.
And detected in ZTF. So with the modeling, you've got the size of the shell, the velocity as well, and an idea of when the explosion happened before,
Exactly.
when the ejection happened before the explosion of the supernova.
Exactly.
So what do you think we could see in light curves using LSST or stuff before the explosions? This should be something we should look at, right?
Yes.
And to confirm if you're modeling, to use these 2 point of views and double check the modeling, right?
Exactly.
Did you check that for the TF?
Yes, I went back to 3 years, I think, but paying more attention within 1 year of before the explosion to the non-detections or the like archival data of ZTF at the location where the transient was found. But we didn't find anything. And actually there was a study that shows that in order to find pre-eruptions, you would need quite nearby objects with ZTF because there is the 21 limiting magnitude. But with LSST, at least in the coordinate images, that goes, it's expected to go to 27 mag in the G-band, you would expect to find this kind of eruptions right before the explosion. Now, how the light curve would look like, I don't know if it would be just a bump or it would be like a slow rising and then the actual explosion of the supernova. So I don't know how it would look like, but you would expect to see it in the images.
Because you can have from your modeling, you could have a time scale, right?
Exactly.
Of the time of the disruptive ejection.
Exactly.
Good. Very nice. Thank you.
Do we have other questions in the room or online? Okay, so in case you want to continue the discussion, I invite you to go to the cafeteria for a scientific coffee. And we can speak. Thanks, our speaker again.
Thank you.
And I also invite the PhD students who want to register their presence to come here so I can note it.
How was it good? Good, good. Hello, thank you for coming.